Hi class, let's go over this extra practice worksheet from Module 8. This is our non-parametric module. We have 5 questions. I will work all of these in R. Well, the first question, using the Golub data and an appropriate Wilcoxon 2-sample test, find the genes whose median expression values are higher in the ALL group than in the AML group. Use FDR adjustments at the 0.05 level. How many genes are expressed higher in the ALL group? And then we want to find the gene names for the genes with the 3 lowest p-values. All right. Well, we can begin by clearing all of the saved objects. Now we need to load the Golub data, and we have this gol.fac that we use throughout the semester. We know the ALL group and the AML group have different numbers of patients in them. And so we're going to be using a Wilcoxon rank sum test. We can run. You can see I have used the apply function. Here I have called wilcox.test. I've used this factor, and then I have specified alternative is greater. Now, we need to apply this Benjamini-Hochberg correction, or FDR method, and so that is here. I have used this p-adjust that we learned in the last module. And then we can figure out how many genes have this adjusted p-value. Really, we know for Benjamini-Hochberg it's called a q-value, but in any case, we're looking for less than 0.05. The answer is 407. Okay, well, the only thing left in this question, find the gene names for the genes with the 3 lowest p-values. The gene names are in the Golub.gnames matrix, and so we can find them here. Fantastic. Let's move on to number 2. So I will clear my saved objects. I'm working again with the Golub data, so I will begin the same first 2 lines to load it and then define gol.fac. Okay, we want to apply the Shapiro-Wilk test of normality to every gene's expression values in the AML group. How many genes do not pass the test at alpha equals 0.05 with FDR? This is the Benjamini-Hochberg adjustment. Once again, I'm going to use the apply function. We can see here, so here the function I have used Shapiro test, and then I have only looking at the AML patients. Once again, we can apply this p-adjust function, and then we can figure out how many, after we have adjusted for multiple hypotheses, would we reject the null? Now, in the Shapiro-Wilk test, the null hypothesis is that the data come from a normal distribution. And so we have 225 for which we would reject, meaning the data do not come from a normal distribution. All right, number 3. Well, once again, we are working with the Golub data. Gene HOX-A9, homeobox A9, can cause leukemia. This is in their original paper. Use an appropriate Wilcoxon 2-sample test to test if, for the ALL patients, this gene, HOX-A9, homeobox A9, expresses at the same level as CD33 gene. All right. Well, first of all, we need to figure out what row do we have these 2 genes. So we can go to the Golub.gnames matrix to figure this out. We are looking in row 1391 for HOX-A9, homeobox A9, and row 808 for CD33. Here, We are looking at ALL patients, so the data are paired. We can use Wilcoxon sign test. We can use Wilcoxon sign rank test. Maybe I'll just go through both of them as an example or as a remark. So first of all, the Wilcoxon sign test, we know this is a binomial test. We create this vector diff. These are the pairwise differences where we take the HOX-A9, homeobox A9, and CD33 genes, ALL patients. Then we can apply the binomial test. You can see this p-value is very small. So here we would reject the null that the median of the D's is 0. This would say the two genes do not express at the same level in the ALL patients. But we know the Wilcoxon signed rank test has more power because it takes into effect the magnitudes of the differences. So let's look at that test also. We have to select paired equals T. We get this warning message because there are some patients in the ALL group for which the two genes express equally. And so we have in the difference, in fact, we can look at it, in the difference vector, we have some zeros. Let's see. Before I continue, let me make the remark that we do have a statistically significant test. So we would, with the signed rank test, we would also reject the null as we did before. But if you're concerned about these zeros, what could we do? What I did is I created this new vector diff2 where I took all the differences that were not equal to 0. The length of diff2 is 3 less than the length of diff. Then we can do the Wilcoxon sign test on this vector where I have removed the zeros. I still have a very low p-value, which gives me a statistically significant result. We can confidently say that the two genes express differently in the ALL patients based on this data. All right, fantastic. Let's move on to number 4. Here we're using a data set, UCB admissions. It contains admissions decisions by gender at 6 departments at UC Berkeley. Oh, that's where I did my postdoc. Well, for this data set, carry out an appropriate test for independence between admission decision and gender for each department. What are your conclusions? Well, first of all, let's figure out what's going on with this data set. So here I'm just asking for help on this data set in R. We can see it's a 3-dimensional array. We have admitted, rejected, male, female, and then we have 6 departments. This data came from 1973. Maybe let's just ask what this looks like. UCB admissions. Here for each department, we have this beautiful 2x2 table. Well, we have 2 choices here. We can either use a chi-square test for each table, or we can use a Fisher's exact test for each table. Let's just try one department before we use an apply test. So we know we can use chi-square test provided the expected counts inside the 2x2 table are reasonably large. So let's just look at the first department. You see, here's the expected. Oh, those are all quite large. The chi-square test is reasonable here. We can apply the chi-square test. This is just the first department. You see, this is very significant. So we would reject the null for department 1 or department A as it is listed, that the row and column variables are independent, and we would declare there is some dependency here. There is some relationship here. Now, what would happen if we did Fisher's exact test on this first department or department A? Well, you see we get a different p-value, but we still have a statistically significant test. So far, well, we have 6 departments, A through F, but we would say that in Department A, we reject the null that the row and column variables are independent. There is some relationship between gender and admissions. Okay, now we can use an apply function to work with all 6 departments. So first, we can look at the expected count. So we've already done Department A, but it's fine. We will look at them all together. Sort of scanning this, I don't see any values less than 5. So it would be reasonable to do the chi-square test on all 6 departments. We could also do a Fisher's exact test, but maybe I will show both of them. So first, for the chi-square test, I'm using the apply function, and then I'm storing the p-value. We can look at all of these p-values. We found already this one, Department A, we reject the null. The other ones, this is 10 to the minus 1, so move the decimal place over by 1. Those are all pretty large p-values. So for Department B, C, D, E, F, I fail to reject the null. I cannot say that there is a dependency between admission and gender. Well, we could also do Fisher's exact test if we wanted to. Really, we only need one test here. But you see with Fisher's exact test, this one we found earlier, statistically significant. And the others, you see there's a 10 to the minus 1. So move the decimal place over by 1. We get the exact same result. The p-values are different, but we get the exact same conclusion. So really, either option is fine here because of this. The expected frequencies within each 2x2 table are large enough to use the chi-square test. Last question, number 5. Here we get to program a permutation test. So we have 2 random samples, x1 through xn, y1 through ym. And the population variances are sigma x squared, sigma y squared. We want to know, are the population variances equal versus is sigma x squared, so the variance from population x, less than the population from variance y. And we can use a permutation test. The statistic here is the ratio. You take the sample variance of x divided by sample variance of y. Okay, so we want to look at the CD33 gene and see whether the variance in the ALL group is smaller than the variance in the AML group. So the ALL group will be my X, capital X, and AML from population capital Y. Let's get started. So as every time when we begin with Golub data, here are my first 2 lines. And then the data is in this row 808, okay? Now, first, I can calculate my observed statistic. We take the variance coming from the ALL group divided by the variance coming from the AML group. This is sample variance. Now is when I can start doing my permutation test. So we will do 2,000 permutations. First, let me just have this empty vector where I will store all of my observed statistics. And then I have this for loop. Here, this data.perm is some permutation of our data. You see it has the same length as our data, and then it's just some reordering of the data. Okay. Then, for this reordering, I calculate this statistic. If we look at the alternative hypothesis, it's that the variance of x is less than the variance of y. Now move down to the sample statistic. We would be interested in the proportion of the sample statistic from our null distribution that's less than the observed statistic from our sample. So we can calculate that now. We get 0.0455. Well, this is less than alpha is 0.05. So at the alpha is 0.05 level, we would reject the null. And we would claim that the variance of x is less than the variance of y, at least from our permutation test. Well, as a remark, what would happen if we run it again? Okay, now we have an even smaller p-value, still statistically significant. We run it again. We run it again. We run it again. Okay, well, you notice every time you run this permutation test, you're getting a different p-value. Of course, you have a different collection of 2,000 permutations. But really, either one we choose, we get a statistically significant test. And so we would reject H0. It seems the variance of x is less than the variance of y. This is the end of our extra practice. Let me put all of this into a file for you with my conclusions, and I'll upload it to our Canvas course. Thank you so much, class.